Welcome to the Solace webinar. Our speaker is Sumeet Puri. Sumeet is the Senior Vice President for Global Systems Engineering here at Solace. And he is quite experienced in all of the various large architectures and is going to be talking a bit about digital data rivers, or how we deal with information in motion. Sumeet has worked with large industry scales in the telecom space, and is also quite well versed now in IoT, in big data, and has worked in the financial industry in making sure the data moves and is available to all of the places that are out there. Okay, well, Sumeet, thanks for joining us today, and I will turn this over to you now.
Thanks, Dave, and welcome everybody one more time. So today we are going to talk about the concept of digital rivers and open data movement using the metaphor of rivers and how rivers basically have caused human civilization to progress over the years. And when we apply the same concepts to IT, how can we use these concepts so that data flows and it benefits our ecosystems, it benefits our applications, it benefits microservices, API ecosystems, big data systems, by assuming that data is flowing where we want it, when we want it, right? So that is what I'm going to cover today. So some connectivity issues here. Apologies for that. Okay, here we go. So can everybody see my slides? The first slide?
They can't talk back to you, but yes, we can see your slide.
Okay, sounds good. So advancing now. So starting with the concept, right? So a little bit of a history lesson here. So rivers have been extremely important in the development of civilization, as all of us know. So the four great civilizations, from the Egyptian to the Mesopotamian to the Indus Valley civilization and the Chinese revolutions, Chinese civilization were all around rivers, right? So I'm going to use this metaphor as we go further, because rivers mean what rivers have meant to civilization. They mean the same when they are digital to applications, as we'll examine, right? So we were recently in a pivotal webinar, in a pivotal meetup actually, and the Solace CTO was asked this question about explaining data rivers in detail, and the interviewer summed it up in a very nice way, which I put as the quote here: ask not what your app can do for your data movement layer, but ask what your data movement layer can do for your application. So at Solace, that's the problem that we are solving. That's the problem that application developers face from time to time, that how do you make sure that data is always available in a streaming manner to you, and how can you make sense of the data and do interesting things with it, okay? So quickly advancing through some of these, and here, just looking at what do we expect from this data river concept, and I understand it will be a little bit abstract for you at the moment. I just want to lay the concept of flowing data here, and we'll get technical from there onwards. Okay, so we expect the rivers to handle bursts, right? So of course we expect the rivers, as we saw earlier, that data should flow from one application to the other, from source to destination. Data should flow from event sources to data lakes. But then a good data river should have the ability to handle big bursts of data. So this could be peak hour people logging in. This could be income tax filing on a particular date. But burst handling is a key difficult requirement for a data river to handle. Another interesting requirement, as you can see on the slide, is load balancing. So having the ability to balance this load across multiple consuming applications. So you have data coming in from a producer in a big burst, and how do you get this information sent to multiple consumers in a load balanced manner so that they can get the data at the speed that they can consume it. And again, extending the concept further, throttling is another difficult problem to be solved. So the throttling problem would be, how do you make sure that these slower subscribers that you have are not overwhelmed with the data? So how do you dam your river such that the subscribers get the data at the rate that they can happily process, rather than just dying as a result of overflows? Okay, so taking the discussion further, and I ran out of pictures, otherwise the whole slide would have been picture after picture, the whole deck. So looking at some other areas, so functionally, a data river has to have quite a few things it should support. So from message exchange patterns, which we'll examine, request reply, publish subscribe, queuing capabilities, various qualities of service, guaranteed never lose a message style messaging, direct request reply style messaging, topic-based routing, or from a REST perspective, URL-based routing, and then multi-protocol interoperability, come in from any protocol, go out from any. And some advanced features like subscription management. So you don't know what subscriptions your subscriber is or the subscriber doesn't know what subscription he's authorized to take. The server-side provisions, subscriptions, provisions the topics that you want to listen in for you, right? From a non-functional capabilities, of course, burst handling, slow consumer isolation. So if you have certain consumers who are slow, how do you deal with them? Do you make sure that the well-behaved producers or the well-behaved consumers become victims to these slow consumers or otherwise, right? High availability, that's a given. Disaster recovery, elastic scalability, especially with the advent of the cloud, has become much more important and possible. Multi-data center, again, with the cloud, so certain applications live in certain data centers while certain other applications elsewhere. So all of these features as you go, WAN optimization again, and another one, security is table stakes. So these are the requirements for data movement, if you will, right? So at Solace, that's basically our requirement traceability matrix, that how do we make sure that all of these capabilities are supported in a single product, right? And also how they are deployed from an architecture perspective, what's the know-how to use these capabilities in an architecture. Right. So some of the major industry trends that are shaping these requirements are here. So not to belabor the point, but from the move to the cloud, from the advent of IoT, sensors becoming cheap, and data multiplying many folds, big data lakes needing this data and making sense of this data. These major trends are defining the requirements of the digital backbone, or in other words, next generation messaging, right? So again, this is just to summarize the requirements here and some of the newer IT paradigms that we deal with today. So microservices have become very topical, and rightly so. So how the service-oriented architecture has evolved into a microservices mechanism will be discussed as we go further. Batch to real time also is an interesting trend that we are observing, and bimodal IT similarly is another one. So as applications become more and more distributed, as APIs become more and more popular, connectivity is the new thing. So more and more applications are leveraging connectivity to do interesting things. Right. So looking at these requirements, let's look at the digital river from the eyes of messaging. So what messaging was earlier and what Digital River now is. So in the meantime, I've got a question from the audience which says, is this a framework, product, or a solution? So Solace provides a product, and together with the product, we plug and play into many frameworks and realize multiple solutions. So as Solace, we provide an open data movement or a messaging product, which meets all of those requirements, and we'll examine that in more detail. Right, so the problem statement is you need to have omni-channel delivery for digital problems. So from iPads to browsers, to kiosks, to B2B interfaces for your customers. Straight-through processing has become table stakes again, so no more paper. Although quite a few systems don't have paper or haven't had paper for a while, we still encounter many, many systems where there are manual processes that are being invoked, and processing is not straight through in even the most sophisticated of organizations. Event-driven architecture is finally gaining a lot of popularity. The concepts are not new. They've been around forever. And now we've seen event-driven architecture's popularity, even with Gartner recognizing event-driven architecture as a concept in an interesting way, which I'll explore. And microservices are a realization of the event-driven architecture paradigm, where you have events happening and microservices consuming those events, making sense of those events, and offering business logic as a result. And while data is flowing through these different systems, from the channels to the straight-through processing layers to through microservices, and they could be flowing within your data centers, they could be flowing through the cloud, big data both in motion and big data storage feed off this river, right? So data lakes are feeding off the data river, and often like parasitic listeners, right? So we're just talking about tapping data as this data is moving along, right? Also looking at an analyst's perspective, or rather multiple analysts are painting this picture, that in the next 9 to 10 years, a lot of systems would be moving to the cloud. But as you look at the analyst reports, not every system is going to move to the cloud. In fact, most analysts are predicting that a third of your systems would move to the public cloud, another third will move to the private cloud, and the rest will remain on-premise, right? So legacy systems or mainframes or AS400s are possibly not going to move to the cloud anytime soon. So, which means that the future is hybrid, and you don't have to agree with the proportions. You may say that no, only 10% of your systems will remain on-premise, maybe 20% will be in the private cloud, everything else will be in the public cloud. That's all fine, but the future still is hybrid. You would need a mechanism for all of these three to work together. Okay? So what Solace does for you is we are the on-ramp to the cloud. So let's say you are in your data center and you want to get to the cloud and you haven't made the selection of your cloud vendor yet. Maybe you have a shortlist, maybe you have certain capabilities from a certain cloud vendor that you would like to select. So to move to the cloud, you need a mechanism that integrates these different cloud systems with the on-premise systems that you have. Essentially, you need an on-ramp to the cloud. So Solace provides you that. We are the on-ramp to the cloud. As a messaging fabric, we integrate different applications that you have on-premise in a standards-based manner to the different applications you will eventually deploy, or probably you already have deployed in the cloud of your choice. Okay? So taking this concept further, just defining what Solace does. So Solace is a provider of open data movement, and open data movement means that moving data following open standards. So following standards like REST or MQTT or AMQP or any of these standards, and using these standards across any data center, across any cloud. So complete agnosticity from a deployment platform perspective, moving data from anywhere to anywhere using open protocols, right? So that's essentially what Solus does. And that's the definition, again, of the digital river. So if you look at it from an evolution perspective, and here we've started to define Solus a little bit more. So you would have legacy applications or even newer applications in your data centers, and these applications would often be integrated with some sort of an EAI or some sort of an ESB layer, where you would be following standards like JMS, or if you're a Microsoft shop, then various .NET standards or CORBA back in the day. And these applications would sometimes use ESBs or integration layers from some of the vendors that are mentioned here below, right? So information flows on-premise in an integrated manner. Messaging becomes an important part of your ESB layer. So if you pick solutions from most of these integration providers, you would have some form of messaging. Many a times it is Solus as a JMS broker, or it could be IBM MQ, or it could be TIBCO EMS, or WebLogic JMS, or Kafka in recent times. You would have some sort of messaging which connects these applications with each other, and the ESB layer works as the transformation or the adaptation bus. Again, if we extend this whole concept into the new world, where we've got big data coming in, we've got cloud deployments, we've got IoT contributing to the data in a big manner, and then API platforms for the API economy contributing to digital data, what you would see is you need to extend this data movement fabric into all of these newer domains. And as you have these new domains integrated, you would need their newer standards like MQTT or AMQP to integrate these standards. So MQTT precisely for IoT. Many cloud systems, for example, Microsoft is big on AMQP. For big data, you again could do Spark streaming over MQTT, or you could also use GMS to go into Flume. APIs would be all about REST. So you need a fabric, a data river that supports all of these protocols and can then integrate your systems, which could be partially in the cloud. So we've seen applications where the front-end layer, the front office layer are in the cloud, and they integrate with the core backend layers or the back office layers, which are still in the legacy data centers. Similarly, the API gateways, the API layers could be exposed through the cloud. So an end-to-end fabric of flowing data, and as data flows, your big data lakes just become consumers to that. Okay. So again, taking a pause here, and now we'll go a little bit further to explore the concepts of APIs and microservices, and how do they relate to messaging, how do they relate to data movement, right? So some of the common patterns and protocols which we've experienced with some use cases. So interestingly, Gartner also pointed this out earlier in the week, but data movement is not just request reply. So we come across many API discussions. I've personally been involved in quite a few where APIs are understood as request reply, REST-based calls, right? So if it is a flight ticket booking, I make a ticket booking as a RESTful call, and I get the ticket booked, right? So simplistically speaking, that is what it looks like. But there is more to it. There is more asynchronity, right? So why does every API, why does every system have to be request reply, when if you just look at the possibilities of two variables, so 0 or 1, in or out, you can have these 4 patterns. So Gartner doesn't yet do a magic quadrant for messaging, so we did one, which is data movement patterns are in only. So I capture the data and don't do anything. It's in-out, which is request reply. It's out only, where the server side could be publishing information. So publish, subscribe kind of APIs. You're sending temperature information. You're sending bus arrival information. And there are many apps out there. There are many consumers out there who are consuming that information. A very common implementation for this is sending stock ticker pricing or foreign exchange pricing, where you have this information going in, right? So out in is the one which is basically the server side invoking a request to get more information from the consumer, right? So, for example, a firmware upgrade being pushed into an IoT device by the server side. So, as I said, Gartner has recently published this again, where they are also saying that request reply is not enough for an event-driven implementation of APIs. You would need more than that. You need a messaging fabric for your microservices. You need the ability to have asynchronity weaved into your architecture, right? So CQRS, or Command Query Responsibility Segregation, is a pretty interesting concept itself, which works hand in hand with the event-driven architecture, where you say that the command path or the ability to save data, ability to insert data, is decoupled from the query path, where you're just we're just querying information using in-memory data grids, etc. Okay, so applying these architecture patterns to microservices. So how do we look at microservices? So the API definition of microservices is some functionality which is exposed via REST or maybe another protocol. Conceptually, we look at it, so I have an electronics engineering background, and I like to think about chips and microprocessors. So to me, a chip which does some business logic, some fixed functionality, has some interfaces which it is exposed with, and it is integrated into a board using certain wires on the board, as you can see. So the chip which is exposed by these different standards is the microservice. In the case of modern software, these endpoints are REST, AMQP, MQTT, because with these we get all the message exchange patterns. The glue which binds them to the board and orchestrates them with the other chips is the data river, which is Solace, which provides these endpoints. And the business logic is what you implement in your mechanism, in your systems, whichever way you like, right? So just a way to look at microservices and understanding them in a simpler manner rather than the entire API economy mechanism, which is all good. So all the governance, all the billing, all the other information are layered on top of this. So that's all still relevant. Now, from a Solace perspective, what does Solace offer? So Solace offers a multi-protocol messaging data movement backbone, which does all the things that we've talked about above. So it allows you to send and receive information from any protocol to any protocol. So you could be sending messages via REST, and you could be consuming them as GMS messages right at the bottom here. Similarly, you could be publishing information via AMQP, and you could be receiving them as MQTT on the sensor side. So essentially, coming in from any protocol, going out from any protocol, and the protocol translation is done by the messaging fabric. You can use any of these open protocols, so pick the open source PAHO APIs or the open source Cupid APIs, and they will take care of the interoperability. Similarly, you could use any of the Solace specific APIs, or you can implement your application on Pivotal Cloud Foundry or any other Cloud Foundry using Spring. Solace will tie everything together for you from a data movement perspective. So this gives you the ability to have your application done in any any language, any platform, any cloud, and still be modular enough so that these things can talk to each other, right? So implementation of your API versus your channel implementation could be totally different. So exploring some patterns that we've come across in this whole picture. So rest assured and the Veta pattern are something that we commonly come across as to why is messaging required? Why is a digital river required to sit behind an API, right? So what is messaging? Again, many of you would know messaging, but just covering it for users later. So a message essentially is a header and a payload. And as far as the payload is concerned, it could be binary, it could be video, it could be text, it could be JSON, it could be anything. The header is a topic, or if this is a RESTful call, it's a URL. And as you can see, it's a / separated string, right? So it combines various segments, and these different segments are such that you can route on them. So you can do wildcard-based routing using these segments, right? So here is an example of an EDI message. So if you're familiar with the electronic data interchange in the logistics domain, this is an 850 message where you can have like a purchase order or an advanced shipment notification, and different elements on which you would want to route information of this advanced shipment notification or purchase order or any of these messages are in the URL. The version number is also there in the URL, and you can, as subscribers, as you can see, use certain wildcards. So you can say that give me all the orders of Coke. I'm not interested in the orders of, let's say, Sprite. Only give me the orders of Coke. So I use a greater than wildcard. MQTT uses similar concepts but different wildcards. Similarly, the asterisk wildcard is saying that anything related to Coke, whether it is an order, whether it is an advanced shipment notification, I'm interested in that, right? So that's the core concept of topic routing or REST URL routing. Now, if we look at it from a rest assured perspective, so what is rest assured? So rest assured is a capability that when you're sending information in as a RESTful API, there are going to be certain consumers or certain modules in your system which will instantly need to respond to that API call. But then there'll be certain other systems which would be asynchronous, like your big data layers, your logging layers, etc. What you need is you need assured delivery for those guys. So the message comes in as a REST message, but gets automatically queued without any bridges, without any additional line of code, just gets naturally queued for the consumption of these slower consumers, these asynchronous consumers, and assured delivery is provided on a REST channel. What you can also do is that you do not reply with the 200 OK till you actually get the information queued. So what you can see here is data is coming on a REST post. A simple RESTful URL is coming in. That automatically gets translated to a GMS topic in Solus, as we talked about the multi-protocol part. And you can have multiple queues which are then just subscribed to these URLs or these topics, and you can use wildcards. So your order management module would be subscribing to all orders. Your big data module could be subscribing to everything, and so on and so forth. And the beautiful thing is that because the digital river does fan out, does publish, subscribe, does load balancing, all of these things, for fan out or publish, subscribe, you can add newer consumers. So these could be your big data systems. These could be your other new consumers, which you could add again later without modifying your publishers, without modifying any orchestration fabric or any ESB, because messaging will just generate copies and give the data to you. So taking this further, the rest assured concept. Now, there is a pattern which we've started to call the waiter pattern, right? So if you take a step back again from technology and we see how a typical restaurant works, right? So in a typical restaurant, we go in, we place the order, the waiter comes, he takes the order from us, he would do quick validations. He would say, what is the soup of the day? What's the fish of the day? Is it available, not available? So it does a very quick validation, right? And after he's done these validation, he goes and places this order to the kitchen. And once he's done, he moves on to the next table. So essentially, the order taking process is synchronous. So when the waiter takes your order, gives you an acknowledgement that, yeah, I've taken your order. Let me repeat your order. This is your order. And then the order is given to the kitchen in an asynchronous manner, right? However, imagine a restaurant which worked differently, where you take the order, the waiter takes the order, you place the order, the waiter takes the order and goes to the kitchen, gives the order to the kitchen, and then waits for the order to be fully prepared, and then comes and visits you. That's how we've seen quite a few APIs being implemented. Like as a part of the digital revolution that we are experiencing in the industry, APIs are being implemented such that they are completely request reply and they are completely synchronous, right? So if you look at your flows closely, they don't have to be synchronous. You don't have to be implementing APIs like the waiter who waits in the kitchen for the slowest processes to cook the meal while the next customer is waiting, right? So how should a normal waiter be working? As we've discussed before, a normal waiter takes your order, sends it to the kitchen, moves on to the next table, and then once your order is ready, your order is served to you as a callback, right? So when ready, give it to me. And we've experienced this in all sorts of systems. I think the most telling one was a couple of years ago, we were deployed as a part of a tax filing system where the tax filing APIs, which is very easily applicable to this use case, that you file the tax, all you need is that here's your tax filing number, and the tax processing can happen like 3 days later. It does not matter, right? So what you need is rest assured. You send information via REST. You have a quick little waiter application that responds and tells you that it was successful. Your validations, your credit check, any of those things were done. It is all successful, and then it basically moves on, queues the data, right? So here are some results that we saw, and this is not just tax filing. This could be a telco order taking or a preventive maintenance or a maintenance order taking. An order is an order. So without the asynchronous waiter, let's say if this was the synchronous waiter, you send the message. So the validations and checks takes 250 milliseconds for you to process that. Then your typical API platform, mediation platform, or ESB processes that, sends it to the business logic. Business logic comes back, sends it to the reporting system. That comes back, then to the data warehouse. And in future, if you add more systems to this orchestrated fabric, then each of these hops is going to contribute to your response time. So guess what? In this system, the response time was many seconds, which also meant that the throughput was also a function of the response time and primarily of the ability of the ESB. So this architecture has since been transformed to follow the waiter pattern, and Solace is the queuing and the rest assured mechanism in the architecture. So now the information, the tax filing is pushed into Solace. The validation checks is still synchronous, right? Because you don't want to accept garbage. You don't want to accept junk messages and not check any validations. But then these validations don't have disk in the data path. They are done off in-memory data grid, etc. And this is the command path of things where you have information coming in. We quickly send it as a GMS message. In this case, it's running on WebLogic servers. Solace has been used as the GMS bus on the WebLogic side, the REST bus on the channel side. So do some quick validations. after they are done, then you send the messages to multiple queues. And the business logic, tax reporting, data warehouse, all of those systems get that information asynchronously, so behind the scenes. So from a customer's perspective, the response time has increased dramatically, but also the backend processing now has become parallel. Right? So that's essentially the event-driven way of doing things. You had an event, which is a tax filing event. You took that event. The first consumer of the event was a validator. Then you published another event, which is then consumed by all of these other consumers, right? And everybody does their own thing. So tax filing is an obvious example, but as we go into microservices further, we'll explore a couple of more examples. And most of these examples have the ability to get orchestrated in such a manner. So somehow I am stuck on the slide. It's not. Okay, so there's a little latency here. Okay, so another example I can give you is an insurance discussion we had. So just like many architects, I love my coffee, and this was a coffee chat I was having with an architect of a major insurance company globally. So as we discussed over a tissue paper, so you can barely see here, but the top is the UI layer. The medium, the middle layer is the system layer, where you have the different business logic boxes, the waiters and the business logic. And then in the back end, you have all the data layer. And this twisted tissue paper in the middle is the data river. So through our discussion, this was done by the architect of that insurance company. And essentially, to build an insurance system, once you put in the data river that ties your UI to your systems to your data, and information is flowing, this way you can have a very responsive and agile system. So the end realization of this system is what you see here. From the iPads, insurance agents, which were earlier using paper trails for creating new customers, which were using paper trails for claim filing. Now they've been digitized to use iPads. They fill up the forms, they take a picture of your passport, they press the submit button, and this information is sent over REST to Solace, where Solace then sends it to various backends. And this is a multi-cloud system where you have the private cloud and on-premise systems where policy management, customer relationship management systems are. But then you have the document management in Amazon. So all these passports and other documents are being stored in S3. So Solace also sends a copy of the messages to Amazon, where Solace lives as the messaging fabric in Amazon. And similarly, the insurance company has different branches. So in Asia, they have Vietnam and Thailand, etc. So these different branches also have these repeaters, which is software appliances. So Solace supplies both hardware and software appliances for this open data movement, and you can choose the form factor based on your requirements. Right. So as the information comes in, the API gateway does its job. It does the security aspects, the OAuth management, etc., and then information is sent to the right system in realization of the Veta pattern. Okay, looking at it, as I said, we can probably look at any use case, and if we look closely, we will realize that even the most synchronous appearing use cases are not fully synchronous. They can be made asynchronous, right? So here's one example of flight booking. So if you just look at flight booking, an event happens, which is book a flight. So there is a synchronous call to check seat availability. If seats are available, you would basically book the flight for those available seats, and that'll go into the PNR system where your reservation will be created. Then you will make payment, and as you make payment, the payment systems will be invoked. So this entire flow is very request reply, right? So flight booking, as we naturally see, seems to be request reply. But if we look a little bit deeper into that, as we are doing your PNR booking, here new events are being generated, and these events are possibly routed to other asynchronous systems, such as seats selection or meals management. So you just need to block them. The end systems of seat allocation, the end systems of meals management or loyalty management, they do not have to be updated in sync, right? So they can be, even if the meals management system got updated 5 minutes later, it's no problem, right? So if you just look at any workflow that you have and you break it into sync and asynchronous components based on what really has to be synchronous from a consumer's perspective, you will be able to have these events done, which are only the synchronous events which must be synchronous will be impacting the response time. The other aspect to look at here is, as these events are being generated, so some of them were generated by the channel, they went to their consumers such as the PNR system or the seat selection system, then further generated events which could be payment events or which could be analytics events, and these events then end up going to their respective consumers. So as long as your events have the correct topics or the correct URLs and the relevant payload, all you have to do is throw them into the river, and the river basically will send it to the right consumer because the consumer is subscribing to it. So you don't need a heavy-duty ESB or an orchestration mechanism in the middle. These events are orchestrating themselves based on the metadata that you put onto them, which is the URL or the topic associated with that. And furthermore, as they are going from their source to their destination, they also get governed, because what the data river also enforces, and you can do that with Solace, is ACLs. So access control lists of which event should go to which consumer. So the data warehouse can get everything, but the payment servers, the payment gateways can only get payment data. They don't get to consume seat selection or meals information. Right? So again, a conceptual view of how you could break any flow into an event-driven architecture, and then also expose it over multiple protocols. So these could be REST, these could be AMQP, or any of those protocols. Okay. So looking at it a little bit further from topic routing, URL routing, or a payments-based solution here. So I've recently been involved in architecting the solution. So what you see here is, here the point of sale systems are being modernized so that they're not using dial-up networking anymore. They are digitized. And this particular payment provider has two kinds of transactions. Some of them are with a card, so like a debit card or a credit card kind of mechanism, or Apple Pay style mechanism, where the terminal has to take that information in. The others are electronic transactions, where you fill up a form, you fill up your credit card number, and based on that, the payment gateway will be invoked. So if you look closely here, the payment gateway is sending the information, the channel is sending the information to the payment gateway through Solace. So Solace, again, acting as a digital backbone, is exposing a REST endpoint, and you get this URL which contains like my bank, this is a payment message, who's the merchant ID, is the mode of payment with or without a card, that means is it e-commerce or with a card, what's the type of the merchant, etc., right? Do whatever you want, put the topic structure to whatever you want to route on. Then in the core backend, which is your sync layer, you could have your ESBs exposing services. You could have your business logic and app servers. It could be POJOs. It could be Spring. these guys are subscribing to messages which were published as REST over GMS topics. And here, the GMS topics also use wildcards. So certain modules will get information such that is this a card-based transaction or is it a transaction which is e-commerce? So routing will be done by Solace, essentially the event orchestration that we just talked about. So the right subscriber naturally gets the event and then does its business logic, which in this case is talking to the payment switch, right? So that's your core path. But as I said earlier, as your data is flowing through the digital river, a lot of these other consumers on the side, which you see at the bottom, get hold of this information. And some in a Lambda architecture mechanism, that means there is two speeds for that data. Some is fast, some is slow, right? So the monitoring information, for example, could be slower. So the leftmost part is the leftmost component, which is Splunk in this case, is just subscribing to monitoring messages, right? And these were actually published over MQTT. So you get this information as monitoring data down into your analytics platform. Similarly, your fraud detection and your big data systems get the right events that they are interested in. Right. So as you can see, there are multiple examples we've covered, from insurance to payments to airlines, where the same concepts are being used. And taking the concepts further, now we are going to talk about a little about CQRS and event sourcing, right? So as we talked about CQRS, command query responsibility segregation, here again you can see that from a user interface, there are two mechanisms, two data paths. One is the command path, the other is the query path. And the query path is being modernized by using more and more in-memory data grids, etc. The command path is what we've just discussed, the rest assured capability, where you have information for updating or inserting into the backends. You again need a messaging fabric and a full-on messaging fabric with queuing, with burst handling support, rather than just an API. So that's again where you would use something like Solace as a data river to realize the CQRS pattern. So another example of this is telcos. So Solace is the digital backbone of quite a few telcos. So I'm going to talk about some. So Airtel, for example, has had their prepaid response times in India under heavy burst massively reduced for top-up requests. Another example that I'm going to talk about is on this slide. So this is not really Airtel, but again, using the CQRS mechanisms for a customer 360 application. So mobile first was used as a front-end framework, initially tightly coupled to the back-end systems. So once we've started to engage with the customer, the data river fabric was laid. So the mobile first applications started to consume REST endpoints via Solace, while the backends were orchestrated through their ESB layer using GMS. So now only aggregated data, only the relevant data was exposed to the mobile framework. The next step was to introduce an in-memory data grid. So from a command query segregation perspective, the command path still goes to the data river, but for the query path, the in-memory data grid basically gets a copy of all the data that is flowing through the river, and now its query, the query speed increases dramatically because the disk in the backend systems is not getting invoked. Similarly, the other event subscribers are complex event processing systems, fraud detection systems, and the Hadoop layer. So again, all of these are parasitic listeners to the information that is just flowing, right? And the future expansion of the architecture is, since the core fabric is there, since the information flows, as the telco is adding new systems, as it is modernizing some of its legacies, they just nicely fit in. All they have to do is they have to comply with the taxonomy of the topics, and then the API layers are also plugging into the same messaging fabric. So the API layer is offering its security, its monitoring, its billing, developer portal capabilities, but the core data movement, like in this case for the dealers, for the B2B links, also goes through Solace. Right? So it completely simplifies your architecture that you have to worry about one technology, one solution, different form factors, hardware, software, whatever you choose for your data to move from source to destination. Right? So just finishing off, Lambda architecture, as you can see here, there are two legs of the Greek letter lambda. This is how we are deployed in capital markets. So, but more than 10 of the top 15 big investment banks run on Solace. So here you see for MiFID compliance how Solace is being used. So all of these upstream applications, as the trades, as the orders in investment banks are coming, they write them to Solace very quickly at low microsecond latencies in this case. And then they have, on one hand, real-time streaming, which is time-sensitive analytics and reporting. And then they also have the big data layers, which is not so time-sensitive, could be delayed by minutes. All of these getting data off Solace. And Solace does the slow consumer handling. Solace does the queuing so that there is zero data loss, but then the faster systems are not impacted by the slower layers. Right? So this is a graph which, just conscious of time, I won't spend too much time on. But what you can see here is this was a test that was done by one of our customers. We do it internally all the time, where you see that the blue line is the publish rate. So the publishers of these trades, which keep going at a very high rate. So in this case, it's 300,000 messages per second. And the red line is the subscribers. So basically, through the test, 1/3 of the subscribers were disconnected. That's where you see the red line drop. And then after a few minutes, the subscribers were quickly brought online. So you see that the red line has jumped above the blue line, which is the subscriber rate. So the input to all the subscribers has jumped up the blue line. Throughout this whole chaos, the blue line stays steady. There is no change to the blue line. That means no matter what happens to your not so well-behaved subscribers, the publishers are not impacted. The green triangle is the queuing messages which got queued and they got consumed. Okay, so if there are any questions on this, I can take them later. But there is a video on the Solace website which describes this behavior as well. So from a big data perspective, slow consumer isolation, burst handling are the two key patterns which the data river has to support. Solace supports this, and as a result is nicely plug and play into most big data systems out there, whether it is SAP HANA or Cloudera or Hortonworks or KDB. Pick your favorite, pick more than one, having information coming in from multiple data fabrics and sending it to multiple data lakes in a standards-based manner. Okay, so again, rivers flow into lakes, or some of our customers, in fact, one of our customers has their big data lake or a data warehouse called Ocean. So sometimes rivers need to flow into oceans as well. So last couple of slides I have here. So what's the end game? The end game is a multi-cloud, hybrid cloud environment where can this data river go into the cloud? Can this data river connect multiple clouds? So that's where Solace is heading as a technology, as a company. So we are heavily deployed on-premise, as you can see. So from GMS applications directly connecting to Solace, or some legacy applications which are on MQ connecting to Solace via MQ bridges, and then newer apps using REST or MQTT or AMQP or any of these newer protocols directly. So that's the on-premise data center part. But then as the clouds are becoming popular, having the virtual messaging ability using Docker container or using virtual message images, basically having a multi-cloud fabric so that cloud-to-cloud information is exchanged, cloud-to-data center information is exchanged, and now you can move applications. So let's say I've come across a customer who was moving from Siebel as their CRM to Salesforce. So So Siebel was on-premise, and Salesforce, given that it is in the cloud, all the associated services with Salesforce were ideally built in the cloud. But then the core applications still stay on-premise. So having the ability to have messaging in the cloud, so that if you're in Amazon, if you use SQS, if you're in Azure and you use Service Bus, how are you going to integrate both of them together? And then more importantly, how are you going to make your applications move from one cloud to the other if you had to? Like the recent case of Snapchat talking about $1 billion with Google, right? So having a standard-based messaging which connects all of these clouds together, which basically takes the worry off you as to where will your application be deployed 2 years from now. Will it be on-prem? Will it move to a private cloud? Will it move to Amazon, Google, Microsoft? Maybe there's a new vendor that comes in a couple of years from now. If your applications are talking to each other using a standard-based messaging fabric, this messaging digital river is then interconnecting all of these clouds together with on-premise. Now you can have applications deployed wherever you want, right? So that's basically where we are headed, and I'll leave you with this picture where we are seeing an industrial IoT kind of deployment, moving data from factories to branches through different clouds, from Amazon to Azure. So if Amazon is good for processing, Google Cloud is good for analytics, you choose what you want to deploy. Solace as the digital river is the orange layer in this picture. The blue layer is the application, and the gray layer, of course, is the networking fabric. So once you have the information there, information nicely flows from one data center to the other. So question I see on the panel is, what's the difference between a message bus and a data river? Data river is almost the same concept as a messaging bus, but in traditional terms, message bus has been used as a queuing fabric or as a GMS fabric. The digital river takes this to a different level where you have multi-protocol support, so REST to MQTT to AMQP to GMS, so traditional to modern, all protocols supported. It also has the ability to go across data centers and across clouds with the same product, right? So same wirelines administratively, same wirelines from an API perspective, end-to-end data movement. But conceptually, it's an evolution of the message bus. We like to call it open data movement, in other words.